Welcome back to week 2 of our course, Boltzmann Law, Physics to Computing. This is the second lecture for this week. Now, as you may recall, in the last lecture we introduced this time sampling method, which works in n space, but it allows us to analyze the response in the huge 2 to the power n space. And what we'll be doing in this lecture is we'll be talking about how the interactions in n space control or affect the response in the 2 to the power n space. Now, just to remind you what I mean by n space and 2 to the power n space, it's like if n represents the number of neurons or these units, and 2 to the power n tells you how many configurations they represent. And the Boltzmann law gives us the probability of each configuration in this 2 to the power n space. But 2 to the power n can be a huge number, and so it is really very desirable to have a method for analyzing the response where we don't have to explicitly work in that space. And this time sampling method that we discussed allows us to work in the n space and yet give us accurate results for the probability distribution in the 2 to the n space. And as an example we took last time was a system with just 2 neurons. And that means n equals 2 and 2 to the n is equal to 4. Again, no big deal. This was meant to be a toy example to just illustrate the principles. Okay. Now, what we want to do in the next couple of slides is try to generalize this a little bit. That is, you see here we had just 2 neurons, so it was easy to write out the energy expression. There was just a few terms in there. But in general, if you had say 10 neurons, then you would be just writing forever. So to write it in a compact way, what you could do is use these summations. So for example, what I've written here is a generalization of what was done here for just 2 neurons. So think of it this way, that you see, let's write it out, all the terms, assuming that there's only 2 of them. So summation r, I could put r equals 1, so I get n1 x1, then put r equals 2, I get n2 x2. Here, with r and q, again, r can be 1 or 2, q can be 1 or 2. Again, if I write it out, I get these terms, the w12, n1, n2, w21, n2, n1. And actually, I'd also get a w11 and a w22 in general. It's just that the weight matrix usually does not have any diagonal terms, that the diagonal terms are all 0. So usually w11, w22 are equal to 0. And for Boltzmann machines, the weights are reciprocal. So w12 is equal to w21. And by and large, in this course, we'll be talking about Boltzmann machines, the reciprocal type, reciprocal Boltzmann machines. Whereas, I think just in one lecture in week 3, we'll talk about Bayesian networks, where actually one of these w's is 0. So w12 is not equal to w21. But by and large, we'll be setting them equal, although often I may write things in a more general form. That would work even if they were not equal. Anyway, but if you put w12 and w21 equal to plus 2 and x1 and x2 equal to minus 1 each, then you'll see this expression boils down to what we had used in our example last week. So this expression here is a general way or compact way of writing these energy expressions. Now what we'll do is describe to you something that's even more compact, which uses matrix notation. So the idea is, well, if you have this n1 x1 plus n2 x2, you could write it in the form of a row vector n1 n2 times a column vector x1 x2. Because the rules of matrix multiplication tell you that when you multiply this out, you'll get n1 x1 plus n2 x2. Now similarly, this last term, you could write it as the product of a row vector, a 2 by 2 matrix, and a column vector. But to see this though, you have to multiply this out and see how it works. So supposing you multiply the first two, then this is a 1 by 2, this is a row vector, so 1 row, 2 columns. This is 2 by 2, so when I multiply them, I get a 1 by 2. And so it's again what I get is a row vector. And the row vector will have as its first term will be this n2 times w21, and the second term will be n1 times w12. Then what I have to do is multiply this row vector into the column vector, and that then will give me a single number. So I'll get w21, n2, n1, that's this, and w12, n1, n2, that's the other one. So that's how you could see that this is really can be written as a product of matrices like this, which can be compactly written as, you know, if n is a column vector, then this row vector is just n transpose. So you could write this as n transpose x plus half n transpose wn. And in general, the parameters that define our system are these x and w. So x is this, what is sometimes called the bias vector, and w is what's called the weight matrix. So for example, if you had say 4 neurons, then of course x would be like a column vector with 4 components, and w would be a 4 by 4 matrix. So what would the response look like? Well, you could of course enumerate all the energies for all the different configurations, which I have kind of tried to put in this plot with 2 neurons on one axis and the other 2 on another axis. So if I look at say this point, for example, it corresponds to 0, 0, 1, 1. That means first neuron is 0, second neuron is 0, third is 1, and the fourth is 1, so on. Right? And then what you're trying to do is plot the probability along the vertical axis, the third one. Right? So you could have also just written all 4 neurons in one line, but then you'd have 16 points along that line. But here we have written it so it's in a 2-dimensional matrix, like there's 4 of them on this side and 4 on this side. Now if you actually put down those numbers and solve it, what you'd find is there would be 4 peaks, which would be the lowest energy states. Remember, the Boltzmann law basically gives the highest probabilities to those states that have low energy. So these are the 4 that have the lowest energy. Which ones are they? Well, let's look at 2 of them here. So first one is 0, 0, 1, 0. So what that means is that your level 1 is empty, level 2 is empty, level 3 is full, fourth one is empty. So 0, 0, 1, 0. Look at the other one, 0, 0, 0, 1. So that's like levels 1 and 2 are empty, 3 is empty, but the fourth one is full. Now if you look at the other 2 peaks here, you'll see that one of them corresponds to 0, 1, 0, 0. So that's what it is, 0, 1, 0, 0. As I said, these neurons, you could think of them as energy levels getting filled with electrons or being left empty. And then the last one is 1, 0, 0, 0. So the first one is full and the others are all empty. So basically what this is telling you is that the lowest energy states all have just 1 electron. As opposed to, you say it could have had 2 electrons, 3 electrons, but what is happening is because of this strong interaction term, this W, what happens is if you try to put more than 1 electron, the energy becomes too high because of the interaction term. And if you don't put any electrons, then the energy is kind of too low, because then you are not taking advantage of this -1. Because of this -1, anytime you put in an electron, there's like an N1x1 or an N2x2. So, and these are negative, so they give rise to a lower energy. So finally, the lowest energy states are those which have 1 electron, but that 1 electron could be in any one of those levels. Now, what happens if I, let's say, only keep nearest neighbor interactions? So we say that, well, 1 and 2 have a strong interaction, but then 1 and 3, they don't see each other. 1 and 4 don't see each other. So what I've done is taken out these 2's, these interaction terms, from when they are far from the diagonal. I'm only keeping the upper diagonal and the lower diagonal. rest are all set to 0. And physically that would correspond to like electrons only interact with electrons next to them, but not if they are far away. So now if we look at the lowest energy states, what you'd find is there are 3 of them. Which are they? Well, look at the first one, 0, 1, 0, 1. So that looks kind of like this. Electrons in 2 and 4, 1 and 3 are empty. Now look at the other 2. This one is like 1, 0, 0, 1. So first 0, 0, 1. And the final one, this is like 1, 0, 1, 0. That's 1, 0, 1, 0. Now does that make sense? Well, you can kind of see why. You see, because of this bias term, of course, it's good to have more electrons, but then you don't want to pay the penalty due to interactions. So what you do is you have 2 electrons, but you put them on alternate sites so that they don't interact with each other. Remember, in our model, we have assumed that the interactions are only with the nearest neighbor. And so all 3 of these configurations kind of minimize energy by having as many electrons as possible without incurring this interaction penalty. And that's why these 3 are the lowest energy states. Now, what would happen if I take off the bias term? So let's say we say, there's a -1 for all 4, but instead for the second one we'll say, let's take out the -1 and make it 0. Then what happens is you don't gain much now by putting an electron in the second state. So when you look here, what you'll find is this state, the one that actually had an electron in the second state, you see there's a 0, 1. So that row kind of gets taken out. So when you put x equal to 0 for the second one, you end up with a picture that has only 2 peaks left, because there is not much advantage now to putting an electron in that second one. Okay. So in general then, I guess what I just illustrated to you was a few combinations of these different x's and w's. And my main point is that x and w kind of determine the state space response. So x and w are actually in the n space, in the sense that we had 4 neurons, so x was a 4×1 column vector, w was a 4×4 matrix. But the response is in the 2 to the power n space, and they shape this response, the x and the w. That's the main message I want to get across here. Okay. Now what we want to do is kind of change our approach a little bit. You see, so far, as you know, we are coming from this Boltzmann law and equilibrium statistical mechanics, where the objective was to understand nature. And nature gave us certain x's and w's. Like the interaction often comes from, say, Coulomb interaction between electrons. So it's the natural interaction that dictates it. And the objective was, well, how do I analyze the state space response that I get? Now, what we want to do is, going forwards, is the approach will be, we want a particular state space response in order to solve a certain problem. There is some application that requires us to solve some problem, and that's what this state space response is supposed to do for us. Now, question is, what kind of x and w will get us there? So x and w is no longer something that nature gives us and we just have to model it. It's more like something that we have to figure out so that it gives us a particular state space response. So complete reversal of which comes first and which comes next. But then you might ask, well, supposing you have figured out x and w, how will you implement them? I mean, previously it was like that's what nature gives us. Nature has already implemented it for us. Now it's like, okay, it's up to us to implement it. So the answer is, well, if you're doing all this in software, so the natural interactions, of course, come from the physics. But when you're implementing all this in software, we can implement any x and w. For example, as I mentioned in this method, you often write a MATLAB code or a Python code to simulate all this. So there will be a line which says Okay, this is how you find these X, you use the X and W to figure out the next state of the neurons. Well, you can put in any X and any W you want, right? Because in software, then it has nothing to do with any external physics. We are not restricted by the physics of anything. So in this approach then, in software, we'd view n as just a binary variable. It's not the number of electrons anymore. It's just a binary variable with two states, and then X and W we can implement any way we want. And just to keep this in mind, what I'll do going forwards is, instead of n, I'll write s. And this is just a change in symbol. I mean, n had two values, 0 and 1. Same is true for s. It also has two values, 0 and 1. That's it. It's just that n has this connotation of being the number of electrons in a particular level, which I had used to motivate it when we got started. But going forwards, we'll just write s. It could really be any binary variable. Now, and so the equations that we have then, these are exactly what I had before, but now instead of n, I've written s. That's all. We keep the x and the w, and the idea is that s is just a binary variable. And the time sampling method is still exactly the same, just that instead of n, I'm writing s. That's all. Now, how could we physically represent these s's? Well, one way to represent it on a digital computer would be, well, if you had, say, a little CMOS device where you have two transistors, one is on and one is off. And the voltage in the middle kind of depends on whether the top one is off or whether the bottom one is off. So we could call this one could be your 0 and this could be your 1, for example. So if you had to write 0, 1, 0, 1, then it could be represented by a string of inverters of this type. That would how the computer would represent it, for example. Another way one could do is what we have been doing so far, thinking of it as energy levels, which can either be full or empty. If it's full, it's 1. If it's empty, it's 0. Now, yet another way could be, you write it in terms of as a magnet. You view it as a magnet. So a magnet could be the south pole could be upwards and north pole downwards, or the north pole can be upwards and the south pole can be downwards. Now, this magnet representation is kind of nice because it naturally carries over into the quantum part of this course. Okay? Because, you see, magnets are actually composed of lots of little magnets. It's a collection of many little magnets, and which have all lined up together because of certain internal interactions. Now, what are these little magnets? Well, actually the basic elemental magnet is the electron itself. So the electron, we all know that it carries a charge, but it also actually carries a magnetic moment. And often pictorially you think of it as if it's spinning, as if you have a spinning charge which gives rise to a circulating current that is giving you a magnetic field. So you could have this spin up or spin down, for example. But the point to remember though is that these electrons, this elemental magnet is actually a quantum magnet, and that requires some amount of conceptual change from where we are. And that's what we'll try to do in the last 2 weeks of the course. But for the moment, you see, we want to stick to classical spins. This weeks 2 and 3. We're just talking of classical spins, and these classical spins you could kind of think of as magnets, if you like, whether it's pointing upwards or downwards. And in mathematical terms, we'd write expressions in terms of like this S, which has a binary variable 0 and 1 with two values, and which you can analyze in 2 to the n space using the Boltzmann law, or you can analyze using this time sampling method that we have been discussing. Okay. So to sum up then, what we have seen in this lecture is how this x and w in n space control the response in this 2 to the n space. What we'll do next is how you can design your x and w so that the response in state space will actually solve a useful problem for us. See you in the next lecture. Thank you.